training computer vision models with synthetic data. It will be presented by Cesar Romero. He is a principal ML engineer at Unity Technologies. Earlier this year, Unity announced a synthetic data engine, as well as perception toolset to generate and analyze synthetic data at scale to train your ML models. Cesar has been one of the leading engineers on these efforts, and today he will give us an overview of these tools as well as how their customers are currently taking advantage of them. Prior to Unity, he spent many years at AWS working on various machine learning services and tools there.
And with that comes the warning that you might hear some toddler noises in the background. And obviously I cannot mute my mic, so sorry about it, but hopefully they're under control. I will attempt to take questions to make it a little bit more interactive. So feel free to type your questions in the chat and I'll try to find good times to stop. Basically, the intro already took care of my second slide, so we're gonna skip. Not quite, I'm kidding. So anyways, but I'm gonna talk about synthetic data and some work that have gone on in or outside of Unity on training computer vision models using synthetic data. Unity is most well known for its game engine. And so one of the things that we're doing in the AI department is trying to make that available to a slightly different target audience, which is not game developers, but ML practitioners that are interested in working around some of the challenges with real world data. If I click on the right slide. And so instead of convincing you of like why data is important and all the things that most people already know, I'm gonna start talking about the challenges. And that's what I mean by the intro already mentioned them. So I'll mention them and I'll provide a couple examples right after. So privacy and compliance, many of you are probably familiar with regulations like GDPR and stuff. And at the core of it, it's about making sure that the data belongs to the users as opposed to whoever collects them, which means you can no longer just freely go and collect data and use it in whichever way you want. And so that imposes some constraints in using real world data. And I'll comment briefly further down how synthetic data sets might be able to work around some of these challenges. And so the second one is biases. And there was actually a recent event that I'll mention briefly. Biases that are in the data, as opposed to like, to put that in context with like a model that has some bias and so on. The last part of it, but a significant one, is related to cost. And it all comes from the time that it takes to collect and then annotate this data. And one of the points that I'm going to try to make is also that perhaps counterintuitive for anyone who hasn't been kind of following computer vision is that actually the costs have gone up. But I'll get into why in a second. So GDPR compliance, hopefully most people understand it. So let's look into the bias a little bit. So here, what I'm showing you is an image that is intended to represent a data set known as the flicker faces. And some of you may already predict where I'm trying to go with this. If this image is representative of the kind of faces that you see in the data set, then you could argue, you know, there's a good amount of variation, age groups, genders, ethnicities. But it so happened recently that actually a whole system, and maybe the details can be part of the questions, is a system that was trained to generate the faces using this data set, and then another one that was trained to upsample and downsample, and some of you know exactly where this is going. The end result was this. And it generated quite the Twitter noise. On the left, probably most humans would recognize this as a pixelated version of what looks like Barack Obama's face. And then on the right, that's clearly not Barack Obama. And these generated a lot of noise. This is just like hot off the press, about a week old. And there was a lot of discussion of like, where's the bias and is it on the people, is it on the data and so on. But the key observation here is that I'm not gonna claim that the game engine is just gonna generate all the faces that you need, but more of the awareness that perhaps there's an opportunity in certain cases where if you're simulating and generating the data that you need, then you don't have to worry about some biases that are in the data that you don't control, but you can only collect. So for that, I'm going to actually show you a concrete example that we worked on a couple of years ago. And the intent here is that the Cedar Bellevue was interested in detecting intersections that were potentially dangerous. And they were interested in maybe training a model that you could consume the camera from footage from the cameras in the intersections in the city and see if they could detect dangerous intersections. But for that, you would have to detect near misses and car accidents. And those are rare, luckily. I mean, sure, they're overall, you could argue that, worldwide numbers are in the millions and it's scary and all these kinds of things. But relative to the amount of traffic that just go across the intersection and the amount of pedestrians can just cross it is very small. And so one of the things that they were interested in doing, and this is a project we did in collaboration with the Center for Computer Vision in Barcelona, is to, what if we simulate that intersection? And actually, some of the images were indeed simulated, made with Unity, so that you could then generate those scenarios intentionally. And then perhaps generate examples so that you could train a model to detect what a near miss looks like and what a car accident looks like. I see someone in the chat put the link to, Alisa, the link to the data set that I mentioned earlier. The other point that I was making is related to the cost, and specifically that the cost of data sets has increased over time in complexity. So if we go back to 2012, when ImageNet and AlexNet became pretty popular, finally CNNs on GPUs and all the numbers started improving, the task was given an image, give me a label. As models have gotten better, the community has gotten more interested in solving more complex problems that are arguably closer to what maybe a human would do or what you would need for, say, an autonomous vehicle. And so we sort of graduated from image classification to object detection to semantic segmentation. And I'm not necessarily saying that you graduate from one task to the other, but you could see a trend of how they kind of increased in complexity at a minimum in terms of what it takes to label one of these images. So now we're labeling pixels instead of bounding boxes. And then you do instance segmentation. So now you need masks for each individual object, not just per class. And finally, panoptic segmentation, which like literally every pixel of the image is labeled with class and instance information. And so as the complexity of tasks goes up, the cost of labeling goes up because the human time that is needed to label these images goes up. And so with that context of some of the potential biases and the cost, I'm going to start talking about synthetic data and how it may help. The key observation here comes from the fact that if your simulation that can be created using a game engine like Unity, it has full knowledge of what it's rendering. Therefore, you can think of getting labels kind of for free. And so all I'm showing here is a very simple walkthrough in like what looks like an office space, where you could generate variations in terms of materials and lighting conditions and positions of the camera. And doing this with the amount of variation that you could do when you're simulating data is significantly harder than if you're just capturing, because your office has one set of furniture. And maybe you could go there a date and then you have to come back and take pictures at night and so on, as opposed to simulating everything. Relative to the other point that I was making on the cost, I want to show you one quick case study, and disclaimer up front, like it's not like this is the rules that govern all synthetic data sets and so on, but we did a concrete experiment and side-by-side comparison using specifically for object detection and using a data set that I'll mention a little bit more of later in the talk that contains several products that you might find in a supermarket. And the thing that these two data sets have in common is, like, first, it's the same task and the same catalog. It's 64 supermarket-like objects or objects that you can find in a supermarket, but they both were roughly created in the neighborhood of about 120 hours. And so in that time, we have a rough breakdown, run numbers and everything. So like this is meant to be to make a point and as an example. The differences in the cost. And one of the things that stands out is that in the real world data, most of the cost goes into annotation, which is not surprising. You basically take a bunch of pictures and then you spend time with specialized tools annotating all this, and you have to audit and make sure and correct potential mistakes and so on. In the case of synthetic, one of the things that's interesting is that then what drives the cost is the content. And it's not something that ML practitioners are typically familiar with. This is something that people that work in the games industry or film industry are much more familiar with. So this is the first point that is interesting, is that you benefit from having that extra sort of diversity in the team that knows a different set of tools that you're typically familiar with. And we recognize that this is also one of the reasons why this hasn't been even more popular before. But you can see, interestingly, that a very important difference is that every image that you take, you have to annotate. Whereas if you create content, And because the game engine has everything it needs to know once it's just rendering that content, you can create the content kind of once, and I'll get, we can comment on what that kind of means, but you can then scale it up, and you don't have to pay the same cost of annotating every single image. And so in the same amount of time, you can generate 1 million synthetic images, or you can generate 1,500 real world images, and the cost of that particular data set looks higher just on the surface, and the exact numbers would vary a little bit depending on who you have annotating images and so on. But even if you lower the cost by outsourcing some of the annotation, you still end up with at least $1 per image for this particular task in this data set, which is still orders of magnitude higher than we were able to generate from simulation. And so that's the takeaway, at least in terms of this particular comparison for this use case. So what I want to do is then, okay, if these are some benefits of synthetic data set, then I want to talk to you about sort of a quick survey of what has been going on in the world of computer vision and as it relates to people using synthetic data sets. And so an important one is back in 2016 in the field of autonomous vehicles. This is work named Cynthia that includes both a data set and an environment made with Unity, where you can run simulations and capture data out of it for semantic segmentation in particular. This comes from the Center for Computer Vision in Barcelona. And this was one of the earlier ones that reach some good results using synthetic data. And there's a couple of observations that are worth calling out here. One of them that are not in this table are that they call out that perhaps to someone's surprise, even though the images that were generated, they are not what you might consider photorealistic, it's not going to fool any human that is not a synthetic image. It was still very consistently, as you see in this table, fairly consistently, able to, once you combine that with the real data set, it outperforms the same model trained on only real data. So even if the synthetic data is not perfect and amazing and photorealistic and all the illuminations and all the complexities of the real world, and the intuitive explanation that they provide is, well, perhaps it's the amount of variation in it that actually helps the model. And this actually has been confirmed by other researchers, so I'll talk about that in a second. They also highlighted that in some classes, like cyclists and pedestrians in particular, is where they saw the biggest gains. And they speculate, so their proposed explanation is that these dynamic elements, they can generate as much as they want of in the simulation, but there's only so many in the particular city that some of these data sets were captured. And obviously different cities have different amount of cyclists or different kinds of roads and different kinds of signs, etc. And so one key takeaway here is that combining synthetic and real better than real, at least as far as this experiment, but they actually did a pretty thorough job of comparing different architectures. Mind you, this is 2016, so some of the architectures might feel like, oh, what are you doing? But 4 years ago. So then comes a year after that, something called domain normalization. Some of you may be familiar with this. So this comes from OpenAI. And what they were trying to do here is train an arm to pick up some basic blocks from a table. And the most interesting part of this work is that they trained the model using 100% synthetic data. So everything that the model ever saw was rendered, and then the model was tested on the real world. And you can see here a quick figure taken from the paper where the images not only are not photorealistic, it's like they're comically cartoonish. And this might be a little surprising, but it's consistent with some of the observations that the Cynthia guys made earlier, the year before. And in particular, they explicitly propose here that what's happening is that the amount of variation that you can generate in the synthetic world becomes a form of noise that forces the model to focus on what actually matters. And then the real world noise, which can come from reflections or different colors or slightly different lighting conditions, they just become a form of noise, and the model already learned how to deal with noise. And to my knowledge, this is the first work that was able to train on 100% synthetic data and perform well. And so that's the key takeaway here, is that synthetic is sufficient. Then we fast forward a little bit to last year. This is from ICCB last year, I believe. So about a year ago. And this comes from Google Research. And so they're trying to train a system to do object detection on grocery data, and which inspires some of the work that I'm going to show you before that I also mentioned briefly earlier. And like the domain randomization work, they were interested in doing this using 100% synthetic data. And so this just shows rendered assets that they use. 64, that's the number off the top of my head of like supermarket objects. And then they generate in, different rotations and occlusions and things like this. And the results actually have some interesting things worth talking about a little bit. So, in the center, you see some prior work, actually, that the same authors had done. Then this is the result of their model, in particular using faster CNN model to train and test it on real data. And then this is the result of the model trained 100% of synthetic data using the methodology that they describe in the paper. And then there's a couple of things that they highlight in terms of what helped them. They refer to domain randomization. And so they like render objects in a number of different positions and rotations and line conditions and blur. And there's so many things that they randomize. In particular, one thing that's interesting is that they compare like randomly placing objects and all this, what you could call domain randomization parameters, versus having curriculum strategy that that places, so it controls the placement and the distance of the object from the camera. So it would seem like objects sort of get smaller over time. The intuition being that smaller is harder, so start from simple and eventually get to harder. I personally think this is kind of interesting to highlight because it's not a very common setup in computer vision. And then the other thing that they call out is that when they replace the real background that were just real world images, and then we're just like rendering objects on top of it, replace it with a completely synthetic background that have all kinds of noise, and that you can see in the paper, that also helped the model. So again, we go back to this theme of like large amount of noise that you can get from the simulation, help your model deal with noise in the real world and perform better. And so in this particular case, their model trained on synthetic was actually better than the model trained on real. And one last example, some of you may be familiar with this, which is then, okay, now we have two examples of domain randomization having positive impact. And OpenAI took it a step further last year. And there's a couple of papers that tried similar approaches, or at least trying to solve the same problem about automating domain randomization. So if domain randomization is about selecting aspects of your world to randomize to help your model, but then you could think about it from a machine learning point of view, that just feels like now you're making hyperparameter tuning even more complex. And so what they set out to do here is find a way to select those parameters automatically, and in particular, it results in sort of a curriculum approach that I'll try to explain with a figure right after this. But at a high level, what's happening is this, where the parameters that influence how the simulation or render produces images come from an algorithm. There's a toddler in the background that generates these parameters. And you have your typical kind of model training evaluation loop that you might have in your hyperparameter tuning. But then here it influences again the updater, the ADR updater, and the loop continues, except every time you're not just selecting hyperparameters for your model, you're selecting parameters for your data generators as well. And one of the things that is interesting highlighting about this work is that they point out, okay, what if we do this manually, like selecting the parameters, and particularly they focus on entropy here. And so like different degrees of entropy. So like the flat lines are obviously fixed, and then the blue lines on both charts is ADR. And if they run ADR, what they observe is that this is also, some of the structure is built into the algorithm, so that when the model starts performing better, you like increase the complexity of the tasks. But like when to do it is determined by the evaluation and the feedback loop into the algorithm. And so what they observed is that the model basically at the end is as good as it gets, but it starts making progress much faster. And you don't have the extra overhead of having to select randomization parameters by hand. We can clarify that later with questions if you guys want. So let me take a quick look. The next thing I want to talk about is what things exist for you to get started if you're curious about exploring this space. I'm taking a quick look at chat and trying to see. Maybe Elisa, I wonder if you have something that you want to highlight of some of the questions that have come up?
Yeah, there are a few interesting questions from Jay Torkett, who
Mm-hmm.
just posted into chat, I think, timely.
When it comes to synthetic data, I see that one of the challenges aside from creating data is defining what data you want to create. Okay, I think that could go in a number of directions. The observation, however, would be that of course the data that you're going to create is going to be very specific to your task. And one way, and you tell me if this is a matter of misinterpretation or I'm like appropriating your question to do something else, but one aspect that is very hard is to decide how much variation and what exactly are the aspects that are worth varying. And so far, there's no textbook on this, but what I've seen is that intuitively, if you think of the aspects of the images that you know are not critical for you as a human even to make a decision, then you should randomize them a lot. So if you go back to the original paper that introduced them in randomization in 2017, when you look at those shapes, any human can recognize those shapes regardless of the color. And so like randomize the crap out of the textures. Don't worry about getting the textures just exactly right, for example. And that's a very, that's a simplistic example, but that speaks to roughly how to decide what are the things that you need to randomize versus not randomize. Let me know if there's a different aspect of that you wanted to talk about, but I just use that as an opportunity to talk about that. Let's see. I'm tempted, in the interest of time, to go a little bit further with the slides and then take some more questions at the end. So I'm sorry for the background noise. I don't think I can control that. So I want to talk about a couple of things that you could do to get started. Look, in some cases, there are existing simulators that you could just use and generate data. And this is the case for autonomous vehicle because it's kind of a popular space. Interestingly enough, it's actually not a space where you see the most sort of impressive results or something that would replace real world data. But there's a lot of interest because there's a lot of money and there's a lot of cost in collecting that kind of data, and it's multi-sensory and so on. And so here you see on the left a simulator called Carla, which comes from the same authors of Cynthia. And on the right, you see the Rsqrd simulator created with Unity. And what you see is that as the car drives through, you basically are getting the labeled images, the frames. In this case for 3D bounding boxes, and previously it was showing depth estimation and semantic segmentation. But in most cases, a simulator ready to go would not exist. And so you might need to author this content using a game engine or a scriptable renderer. And so what I'm showing here in this image is on the left, one of the images generated by our scene using the groceries examples that I mentioned earlier. In the middle, like the same objects with some bounding boxes, and on the right, just like the metadata that captures things like rotations and the coordinates of those bounding boxes, which you need to be able to consume this. And so this is the first piece that we've been working on and we released recently. So this is open source under an Apache license. And in particular, right now, it contains some labelers and it contains the code that is needed to generate the images that you see on the screen. So it's GitHub URL on the slide. Once you have the content, then you probably want to generate the images or the data set, which is not just images, but also metadata. And so that code, because it's just Unity package and Unity runs locally, you can run it locally, but you're likely to scale it up so that you can get hundreds of thousands or millions or whatever number of images you want to get. And so you can do that on the cloud. And I think this is related to something that Lisa mentioned earlier in the call about service that is called Unity Simulation that was announced late last year, with the idea of making it easier for you to grab your simulator and just scale it up in the cloud and generate the images you need and collect the data set at the end, sort of a thing. So the images on the right are taken from the LG car simulator. And then once you have your data set, you want to do at a minimum some exploratory data analysis before you train, because otherwise garbage in, garbage out. And so we have also released a Python package, also Apache 2 license, that knows already how to parse that. It has some integration with the Unity simulation so that it reads the manifest and finds all the files that are relevant. It knows how to parse the format that we're producing because there's not yet a standard format for different tasks. And it comes with a notebook with examples for you to like visualize different kinds of distributions that you might care about. And on the right in particular, we see a visualization of the different positions of the camera with respect to the object or the frame that's being captured. And this is even the kind of data that you wouldn't even be able to get by capturing data from the real world, because it would be kind of ridiculous or very, very expensive to like actually also capture perfect coordinates of where your camera was relative to the frame and so on. And then very quickly, just to run through the object detection example that I mentioned earlier. So on the left, we have actual images that we captured using this product, and on the right, render versions of this product. And so once you have it, then you can generate a bunch of images with random placements of these objects and perfect bounding boxes around each of those. And you see how, again, that theme of there's a lot of variation, but they don't look photorealistic. And just thought that doesn't matter. And so you see intentional occlusions, you see things objects going through others in a way that would be harder than what you encounter in the real world. You see intentional blur and hue and color variations injected on the right side. And this is actually, turns out, one of the benefits of simulating some scene to generate your data. And so if you do that a bunch of times, then you can easily generate millions of images because the content already exists, the assets already exist. You write the code once and then you throw it to the cloud and go ahead. And so the last thing is a quick preview. So on those packages and datasets, we already wrote 2 blog posts in the last month or 2. And a quick preview on the experiments that we're about to release in a blog post coming very soon is that the same model. So this was very clearly inspired by the Google paper from last year. And so the same architecture that they use, trained on about 400,000 synthetic images and less than 100 real images, the model outperformed the one in real. We're still doing a couple more experiments, which is why I'm not putting all the details here. We're crossing all the T's sort of a thing, but there's a blog post coming soon that will contain the detailed results and experiments. And I think with that, we can open it up for questions. And so we can either read them or someone wants to unmute their mic, and I can try to also pick up things from the chat.
Thank you, Cesar. Yeah, please don't be shy. I see a handful of questions in the chat. If you want to just turn on your microphone and hop on them and ask them live, would be great. Otherwise, we can just read them. You know, Alexandria was asking a question that I think probably a lot of people are wondering about.
Yeah, I don't know if you want me to read it again.
Yeah, go for it.
Yeah, so you showed the slide where you had a table comparing the price and the time it took to generate the dataset synthetic versus real. What I was wondering is, in the dataset preparation time process, you break it down in 4 chunks. I assume simulation is the rendering time.
Yes, but actually it's good to elaborate on that a little bit more because, you know, for simplicity, we put some numbers there, but yeah, I can go into some more detail. So, sorry, was there
so the question was what the other 3 mean in terms of synthetic. I'm sorry for interrupting.
Yeah. And actually I will even also clarify on simulation, because in practice, like if you generate just a single data set of 1 million images and you say that's what I'm going to generate and I'm done with it, it does not take 13 hours. It takes like, I don't know, maybe half an hour. But this also captures like iterations, because we recognize that part of getting your scene set up right is also like development process, and you iterate, and then you run simulations, and then you check what you're doing and so on. And so if we go one by one, acquisition in this case we refer to like actually grabbing the product and capturing pictures of the things that we care about, like basically what's needed before you turn them into digital assets that you can actually render. And so in the case of grocery products, it means actually deciding what is the catalog and going and buying it. And then after that, you start going into content creation by different ways of scanning, either in some cases, literally like opening up a box, unfolding it as cleanly as you can and put it in a scanner, and then trying to eliminate lighting off of it and so on. So that creates textures, and then you wrap the textures around the 3D models. And so like measuring is also sort of part of this acquisition and then fits into content creation. And so once you have all those assets, what I'm referring to with annotation is like in this virtual environment, at a minimum, you have to assign some semantic labels to each of these objects. Like what class are they in your taxonomy that you care about predicting, which is why it's not a significant amount of time, but you just have to like, go and double check and so on. And here there's also a little bit of room, which right now, I mean, it's sort of captured by the simulation bucket on the code changes that kind of, let's do one more simulation and so on. For example, things around placement, like you might test different aspects of relative placement between the camera and the object and rotations and things like this. And in this case, we were kind of inspired by that, very clearly inspired by the Google paper. So it's iterating on like the different aspects of the randomization that they mentioned in the paper and kind of implementing it. There's an aspect of these numbers that is obviously not exact, because the intent anyways is that the tools that we're releasing in the Unity perception package is that things like labelers, you just get out of the box. Things like simple randomization placement, you get out of the box. So that as someone creating the scene, as long as you bring your objects, you just have to like select, oh, I want object detection for this, and these are the classes for my object, and you don't have to worry about how any of that, which obviously we had to do ourselves. Hopefully that gives you some.
Thank you. Thank you. Yeah.
Let's see.
A few more great questions. Anybody wants to turn on their mic and ask Manish?
In the meantime, maybe there's, so just reading from the top where I know that I had not read yet. What's best practices can you share? Randomize as many factors as you can in order to create noise in the common synthetic data. Okay, so this relates to what I was mentioning before. I don't think there's like easy rules of thumb. There's no textbook on this, but the observation seems to be that anything that you know for sure should not influence you even as a human, then just randomize the crap out of it. So in Google's project, as well as the 1% in Unity's perception tool, both use relatively simple 3D models. Yeah, while in Google, they scan models. In the tutorial presented by Unity, there are hand models and textures. In the case of more complex models, how would that affect the performance, cost, and time? Which technique is more suitable for Unity scanning or modeling 3D objects? So first clarification that I'm glad that we have technical artists working with us that are actually better at answering this question. I don't think they're here on call. Well, I don't know if they are, but I would argue that the distinction, based on my understanding of the content creation pipeline, is a distinction as between, let's say, scanning and modeling from scratch, has less to do with the Unity and more to do with maybe aspects of the object that you're trying to model. And so there are cases where just making an object flat and scanning it on the regular sort of tabletop scanner is not an option. There are entire companies that are dedicated to scanning, literally. And some companies even specialize in a specific type of assets. And so just to pick one example that I know off the top of my head, there's a company, Quixel, that was scanning a lot of like rock and natural kind of wilderness type of assets that were used in the movie, The Jungle Book. And they specialize on just that. And so it varies a lot, and it's much less about the tool like Unity or whatever other engine, and more about the nature of the assets that you care about.
Can you one more time repeat what was the name of the tool?
Which of the two? So the one that I mentioned last, which is Quixel, which is a company, just as an example that there are companies that exist that are completely specialized just to the scanning process. In general, I would argue that there is no single solution. There's no silver bullet that just works out of the box and do all the scanning. And depending on the complexity of your assets.
Yeah, okay, because I saw that in Google's project, their models, which is like just a box, had thousands of faces, and I thought that might be maybe heavy for Unity because it's real time.
Wait, say it again. Which aspect would you think might be heavy for the render? And then I'll make a comment on that anyways. But
yeah, because their model had thousands of faces, and it's just a box, so it's a very simple model.
Yeah.
So
So one aspect here that is actually worth clarifying that comes up because of that question is that because now we don't have a human in the loop that is interacting with the simulation like you would on a regular game. While it is true that some would not be renderable in real time, meaning more than at least 30 or 60 frames per second, that's fine, because you can anyway scale it up. At the end of the day, these are rendering in a completely headless mode and captured in like a frame buffer, and they go to a file. So when it runs in the cloud, it actually doesn't even matter if it's not in real time. You can take your time and let it take its time to render. And the time that will take obviously will vary not only on the hardware, but also the kind of illumination algorithm that you're using and so on. But it is totally fine for rendering to take more than real time, because you can scale that out by, you know, having many workers in the cloud.
Okay, that's very good to know. Thanks.
Let's do a few more questions before we wrap up. I see there's a question from Manish that.
Yeah, so how do you prevent this one? How do you prevent potential bias creeping? Yeah, with difficulty. So, because I mean, we have to acknowledge, right, we're also humans anyways, and we're making decisions. That's one of the reasons why we also thought very important that from the very beginning, we work on what we call dataset insights, because like no human can look at 10,000 images that came out of a simulation and give you a summary of what is in those images. And so we can obviously put things in place that are going to follow the parameters of random distributions that reflect our understanding of our target, like our test. But at the end of the day, you anyways have to do some data analysis. It's just that the possibility of generating data that you wouldn't encounter in the real world, and the cost of that being ridiculously low, is kind of the point worth sticking to, sort of, or taking home. So a study about the impact of model performance using different render engines. Yes, very interesting. Okay, so sort of, as in work in progress. So let me read the full question to make sure that everyone got it. So is there a study about the impact in the model performance using different rendering engines, for example, a slow ray trace render versus a fast engine, game engine render? So that question is interesting. And the shortest answer I can give you is that people are working on it, like serious people are working on it. There's no easy answer yet. But the reason it's interesting is because intuitively we might think, well, photorealism should matter, because at the end of the day, we're testing the model on real data. And how the light behaves in the real world is typically different than the shortcuts that game engines take to be able to make something look the way it does. And in Unity in particular, there's multiple renders that you could use. And some obviously would take a lot longer to render, but then they use completely, like, or not completely, but like the best sort of path trace light modeling type of particle render, of which I'm not an expert on at all. But I am aware of specifically the Cynthia group. So the Center for Computer Vision Barcelona, who are the authors of Cynthia and also the Cardinal simulator that I showed, I happen to know that they're actually very actively working on it since at least last year. And they've used a number of different renders precisely to test that. Like, if I have the same environments, the same randomization parameters, but then I use completely different renders, how does that impact my model? Because at the end of the day, what you would like to answer is the question of, like, how and when should I use synthetic data? And what we see so far, anecdotic, well, even more than anecdotal, but just based on like papers and so on, is that it seems like, for example, outdoors is significantly harder than indoors. Okay, that's kind of intuitive. There's also a noisier environment, and there's also more movement, typically more objects. Lighting conditions are harder to mimic exactly. But then we also see that in all the examples that have been successful indoors, the realism doesn't seem to matter. And so I would argue that the jury's still out and more research is needed. One of our hopes is that by releasing tools like this, a larger fraction of the computer vision community engages in testing hypotheses using synthetic data sets. Like if I put a number off the top of my head based on my own observation, go to ICCV last year, and maybe 1% of the papers were using synthetic data. And a lot of them are aware of maybe the potential and aware of the limitations of their own process of gathering data. But the ramping up process is, can be intimidating, because as you saw, like it takes some awareness of content creation, and typically ML people, we are not very familiar with content creation process. And so our goal is to kind of lower that barrier of entry so that we can move that number and have more people testing hypotheses and eventually get to answers, to better answers to questions like that.
Let's do one last question, and then I think actually there's some of the discussions of outdoor, indoor environments probably going to be touched on in Rsqrd's talk as well.
Okay, that's interesting. Let me just pick up one more question from here. Sorry if I don't get to all of them. Do you use generic 3D models like cuboid mesh texture wrap similarly shaped objects? If yes, do you also use generic 3D models for human faces? So in the case of, like, you know, the supermarket products, like they're generic enough, but they actually have their own objects because the measurements matter, like the size of the box and so on. At least we created that so that it mattered. So we have distinct objects, even though the shapes are like generic, like a cuboid or whatever. Generic 3D models for human faces. So that's interesting because the work that I've seen in computer vision with faces does not use a lot of synthetic data yet. And that's actually one of the things that we're curious about. But we recognize it's tricky. And interestingly, the work that we've seen is more about generating synthetic faces that look realistic for the purposes of entertainment, as opposed to, for example, generating variations of human faces for the purposes of, let's say, facial expression recognition. So I don't have an answer for how generic can a model be for human faces. How are we doing on time?
I think we should.
Probably a good time, yeah?
I think we should, yeah, switch to the next speaker. And if you're able to stick around for the Q&A and the end of the talks, that would be fantastic.
Yeah.
I know it's going to be in about 30 minutes.
Good, sounds good.